We're continuing here to talk about vectors after the first video. I have written down our definition here to try to save a little bit of time. If you need to pause it so you can copy it into your notes, go ahead and do that. Then I'm going to go on and we're going to define some things here. So first we're going to say the particle's position vector. So this particle that we are talking about, the particle moving along a smooth curve in the plane, and its position, we can think of it in terms of parametrics, is x of t, y of t. And so the particle's position vector is going to look exactly the same. The particle's position vector, I'm going to call r of t. So that's supposed to be an r, and I'll show a little vector symbol over there. And then it looks just exactly like what we had for our parametrics. It's going to look like x of t, comma, y of t. So this is again that idea that we can bounce back and forth between thinking of it as a point or thinking of it as a vector. Secondly, we have the particle's velocity vector is given by, as we saw in the example right at the end of the first video. So it is a vector, v of t, and it's going to be given as dx dt, comma, dy dt. And thirdly, the acceleration, or let me say the speed. So as we have seen in one dimensions in AP Calculus AB, we said the speed was the magnitude of the absolute value of the velocity, and that is true as well here. The speed is the magnitude of the velocity vector. It's the magnitude of the velocity vector. So we write that symbolically as absolute value of the velocity vector. And remember, that's going to be the square root of our v1 squared plus v2 squared. So as we saw before, this is a scalar. So a speed is going to be a number, whereas velocity is going to be a vector. The acceleration vector, which I'm going to write as a with that vector symbol over it, is going to be the second derivative of x with respect to t and the second derivative of y with respect to t. So velocity and acceleration are vectors. And then we're going to define a fifth thing here. We're going to say the direction of motion. So we're going to call this the direction of motion for this particle is going to be just the direction vector, is what we called earlier the direction vector. That is, it's going to be a vector in the direction of the velocity, but a unit vector. So it'll be that velocity vector divided by its magnitude. So that is a unit vector in the direction of the velocity. So I'm going to get a new screen and we'll do an example and see if we can see how this kind of stuff plays out. So I'm going to say a particle moves on an elliptical path. So a particle moves on an elliptical path so that its position, which I'm going to call position at t greater than or equal to 0, is going to be given by, and we called that before, r of t is going to be the vector 4 sine t, comma, 2 cosine t. So that's our position, vector, which we can think of interchangeably as being like a parametric curve. So the first question I'm going to ask is to find the velocity and acceleration vectors. Find the velocity and acceleration vectors. So hopefully this kind of makes sense. The velocity vector, remember we are going to get just the dx dt, comma, dy dt. So it's kind of like doing two problems in one dimension. We just have to differentiate both the x and the y components. So the derivative of 4 sine t is going to be 4 cosine of t, and the derivative of a 2 cosine t is going to be negative 2 sine t. And so that is the velocity vector. The acceleration vector is going to be the second derivative of position. So we say the second derivative of x with respect to t, comma, the second derivative of y with respect to t. And so we get that by taking the derivative of the velocity vector. So the derivative of 4 cosine t is going to be a negative 4 sine of t, and the derivative of negative 2 sine t is negative 2 cosine of t. So that's the answer to part A. And part B, I'm going to ask you to find the velocity, acceleration, speed, and direction of motion at t equals pi over 4. So we're going to find the velocity, acceleration, speed, and direction of motion at t equals pi over 4. So we're going to actually evaluate it there. So let's see what we get. So our velocity, I guess I can say at pi over 4. I think this would be good notation. Our velocity vector at pi over 4 is we're going to plug in pi over 4 into our velocity vector we found in part A. Since the cosine of pi over 4 is square root of 2 over 2, I'm going to get 4 times the square root of 2 over 2, comma, negative 2 times the sine of pi over 4 is also square root of 2 over 2. And so that's going to become, when we cancel the 4 and the 2, a 2 square root of 2, comma, negative square root of 2. So there is the velocity vector. The acceleration vector, also evaluated at pi over 4. We're going to plug in pi over 4 there, so that's going to be a negative 4 times the square root of 2 over 2, comma, negative 2 times the square root of 2 over 2, which is going to give us negative 2 square root of 2, comma, negative square root of 2. That's the acceleration vector. To get speed, remember speed is the magnitude of the velocity vector, or we could also read that as the absolute value of the velocity vector. So using our Pythagorean theorem on our first answer up there, we're going to get 2 square root of 2 squared plus that negative square root of 2 squared. So you can see where I'm getting those from. And if we actually work that, let's see, 2 square root of 2 squared is going to be 4 times 2 is 8. And negative square root of 2 squared is 2. And so that is going to give us a speed of the square root of 10. So notice that the speed is a scalar. It's just an ordinary plain number, whereas the velocity is a vector. And finally, our direction of motion. So what we're going to do here is we're going to take the velocity vector divided by the absolute value of the velocity, or the velocity vector divided by its magnitude. So we found the magnitude of the velocity vector. That was the same thing as speed. So we are going to take our velocity vector, which was that 2 square root of 2 divided by the speed, which was the square root of 10, comma, and then a negative square root of 2 over the square root of 10. Of course, in the AP world, that would be acceptable. We can do a little cleanup because, it makes your math teacher grind his teeth when you don't. We could divide the square root of 2 and the square root of 10 and get that as 2 over the square root of 5. And we could also call the y component a negative 1 over the square root of 5. And I'm okay with that. I don't think there's really any point in rationalizing, although you could certainly do that if you are so inclined. Okay, so what I want now is, let's see, can I fit this on the screen? I'd like you to, I think I can squeeze it in here. I'm going to say part C. Let's sketch the graph of that particle. And then I'm going to ask you to, on that same graph, show the velocity vector. So I'm going to just write it in symbolic form. So we're going to, on the same graph, show the velocity vector. And I think it works nice here because we've got in our position function, we've got sines and cosines. If you choose your t to go from 0 to 2 pi, and if you choose your x window to go from negative 6 to positive 6, and your y window to go from negative 4 to positive 4, we have our x values are 1.5 times or 3/2 times the y values, which is going to make it look like it really should. So I'm going to draw it over here on the side a little bit. You're going to get something, hopefully, that's going to look like an ellipse, and it's going to have the major axis, the longer axis. The longest radius is going to be along the x, and the shortest radius, the minor axis, is going to be along the y. You should get something like that. Now you're going to be able to see the direction that it goes in here, but you're going to also be able to see that hopefully from the velocity vector. So I'm going to put the velocity vector in here in yellow, and if you notice that our velocity vector has a oops, that's not right. Hold on. I want the velocity vector at, what do I want that at? Let's do it at pi over 2. So we're going to get the velocity vector at, did I say at pi over 2? So when we evaluate our velocity vector at pi over 2, our velocity vector was 4 cosine t, so we're going to get 4 times the cosine of pi over 2, which is 0, and we'll get negative 2 times the cosine of pi over 2, which is 1, and so we're going to get our velocity vector is 0, negative 2. Now, we're going to put this on our graph, but we need to know what is the position of this function at time pi over 2. So the position at time pi over 2, if we plug that into the original, way back there up in the body of the question, then our r of pi over 2, we get 4 sine pi over 2, which is going to be 4 times 1, and we're going to get 2 cosine of pi over 2, which is going to be 2 times 0, and so that's going to be at, I'm going to think of this as being a point, so it's going to be at 4, 0. So 4, 0 puts us at this point right here on our graph, and then I'm going to draw the velocity vector in red. It's going to be 0, negative 2. So starting with the initial point right there on the curve, 0, negative 2 is going to go straight down a length of 2. And so this is the velocity vector drawn to our curve at that point. And the purpose of this is to see, and you could have seen it as you drew this when you did it on your calculator, that the direction of motion was going to go this way. But you can also see where the velocity vector is indicating that counterclockwise motion. Okay? All right. I'm going to go on and get a new screen and a new problem here. So we're going to now talk about displacement and distance traveled. Displacement, oops, I guess I'm going to say displacement, distance traveled, and I'm going to also talk about the position. So we're going to compare this to what we do in 1D, and then we're going to see how it's similar but how it's a little bit different when we go into 2 dimensions, which is what we've been doing here with our parametrics and vectors. So if you remember, in 1 dimension, displacement, hopefully you remember this, displacement is given by the integral from, say, a to b of the velocity function. And so this is also known as our net change in position. So the net change in position is we have our position at time A, and then as the particle moves, if we stop the clock at time B, then what this is going to tell us is what we've changed, how we've changed our position. Remember, this is 1 dimension, so you're thinking about moving along, say, a horizontal line, like moving along the x-axis. So this displacement could be positive, could be negative, could be 0. So if you imagine, this particle starting somewhere, maybe it moves right for a bit, then it comes back left, and then maybe it comes back a little bit, but ends up not quite where we started. The displacement is going to be then that net change in position. In the example I showed here, that would be a negative number. Okay? Now, distance traveled, here we want to count like all the steps that we took. So in displacement, when we move to the right and then turn back and move left, those cancel each other out. Distance traveled, we want to count all of the steps, and so we would integrate from A to B the absolute value of the velocity. So that's always going to be a positive number, and it's going to include the steps we went right and add to that the steps we went left. The position, so remember we've talked about this, so our position is going to be equal to our starting place, so where did we start, and then plus the displacement. So how did our position change? So in general, our position, so we're going to say that our position at time B is going to be where we started, our position at time A, plus our displacement, our net change of position, that integral of the velocity. So these are 3 things that come up in particle motion in Calculus AB that are easy to get confused or mix up, and we're going to look at the same kind of things when we do it in 2 dimensions, whether we're considering this to be parametric functions or vector functions. It's pretty much indistinguishable. So let's now look at what's going on in 2 dimensions. So if we say that v of t, and I'm going to write this as a velocity vector, so now we're in 2 dimensions. If that's given by v1 of t, that's our x component, and v2 of t. If that is our velocity vector, and we're going to assume here that v1 and v2 are integrable functions of t. v1 and v2 are integrable functions of t. Then we're going to get a displacement. Then and it's going to be a vector. So the displacement from, we're going to say t equals a, time t equals a, to time t equals b is going to be, and this is now going to be a vector, so I'm just going to write it as d for displacement, and that is going to be, it's going to be like what we did in 1D, but in vector form. So it's going to be the integral from a to b of v1 of t, that's that x component, comma, the integral from a to b of v2 of t dt. And that is going to be our displacement vector. So the position, I think we'll go right here, position of that particle at t equals b is going to be given by its position at time a. I guess I have to write this now as, do I have a good way of writing that? Let's just say its position at time b is going to be the position at time a plus that displacement vector. So where was it when it started, plus that change in position there. And the distance traveled for that particle is from t equals a to t equals b is going to be given as the integral from a to b of the absolute value of v of t dt, which you might remember is going to be this integral from a to b of the square root of v1 squared plus v2 squared dt, which when we were talking about parametrics, we said was the arc length formula, which hopefully makes sense. So the distance that particle travels is going to be its arc length. Let me see if I can give you a little visual over here. I hope this helps with at least the first parts we talked about. So when we were talking about displacement and position. So if we imagine that our particle is doing something like this. We start at time A and then we go to time B. So this is where we are at t equals A, and this is where we are at time t equals B. Then our displacement is going to be that net change in position is going to be that vector that goes from where we were to start with at time A to where we ended up with at time B. That's our displacement vector. And then if we want our position, then what we do is we take where were we to start with. Well, that's where we started, and in vector form, that would be our starting place. So we would take this is now our position at time A, the yellow vector, and then we would add to that the displacement vector d, which, remember, is going to be using our tip to tail rule. That red vector then would represent our position at time b, that position vector, which is the sum of our original position, the yellow one, plus the displacement vector, the green one. Kind of a visual representation of that. Okay, so let's see if we can actually work an example here. I'm going to go to a new screen here. And so our example is going to be, we're going to say a particle has velocity v of t, and I'm going to give you that. A particle has velocity v of t, which is given by the vector t minus 3 pi cosine of pi t, comma, 2t minus pi sine of pi t. And so that's our velocity vector. And then I'm also going to tell you that at time t equals 0, the particle is at the point 1, comma 5. The particle is at, and we can think of this either as a point or as a position vector. It doesn't really matter. I'm going to write it in as an ordered pair so it looks kind of like a point. That's the way at least I imagine it or visualize it. So our first question is going to be find the position of the particle at t equals 4. Find the position of the particle at time t equals 4. So what we're going to need to do, remember position, what we're going to need to do is we're going to have to find the displacement. That is, what was the net change in position of this particle between time 0 and time 4. And so that is going to be given as a vector. And to find that, we're going to integrate from 0 to 4 our x component of the velocity vector. That's t minus 3 pi cosine of pi t dt, comma, and then I run myself off the board here, but the displacement in the y direction is going to be the integral from 0 to 4 of the y component of the velocity vector. So that's going to be the 2t minus pi sine of pi t dt. And that is going to be a vector. Now this is an integral that we can do by hand, so I'm not going to do it here, but if you need help with it, we can maybe do it when we zoom in, but see if you can do that on your own. What I came up with when I got that was the displacement vector is going to be 8, comma 16, so it works out very nice. Now remember, we're not finished because we wanted the position of this particle. And so the displacement, so the position, so our position is going to be our starting place. And at time 0, that was 1, 5, plus the displacement vector, that 8, comma 16. And so what we end up with for our position at time 4 is we're just going to add those components, and we can think of it either as a vector or as a point. It doesn't really matter. It's going to be 9, comma 21. Okay? Now I'm going to ask another question. So now I want to do a part B, and here we're going to try to find the distance traveled. So still talking about the same particle and still on the same time interval from 0 to 4, we want to find the distance traveled. So here what we want is, now remember this is going to be the integral. Let me change colors here. It's going to be the distance is going to be the integral from 0 to 4 of the absolute value of our velocity function, or we also may recognize that from the work we've done with parametrics as being the arc length formula, and that's going to be the integral of, now I'm not going to rewrite it explicitly, but it's going to be our v1 of t, that squared, plus v2 of t squared, which is those components in our velocity vector. Now this is not one that we're going to be able to do by hand, so I guess the good news is you can plug this on your calculator, and if you want to compare it to what I got 33.533 as the distance traveled. So that is the arc length or the distance traveled. Okay, I want to do another example. So I'm going to go to a new screen here, and on this example, I want to find the path of the particle in the example we just did. So now we want to find the path of the particle in the earlier example. So I'll say in the earlier example, the one we just did. So the same information from where we started, that 0.15, to the place where we ended, the 9, 21. So it's not always clear here. I think you have to think a little bit about what that's even asking for. It's really asking us to find, we want to find that position vector, or we want to get what is the position. That is, we're looking for an x of t, comma, y of t. Now, we know from the information we got on the earlier one, we knew the starting point. We said this thing started at the point 1,5, and we also knew the velocity vector, which, remember, is the dx dt, comma, dy dt, and we're looking for the functions x of t and y of t. So what this really is what we would have called in AB calculus an initial value problem. It's really a differential equation with initial conditions, but actually it's kind of two different differential equations with each of their initial conditions. That is, what we're saying is that we know dx dt is equal to, and the x-coordinate of the velocity that we had earlier is the t minus 3 pi cosine of pi t. And we also know its initial condition because it started at the point 1, 5. That means we know that x of 0 at time 0, that was equal to 1. So this is really just a differential equation with an initial condition. And then we've also got a second one. We've got the differential equation dy dt, that is the y component of the velocity function that we had in the beginning, which was 2t minus pi sine of pi t. And we know that its initial condition, its value to start with, was that y-coordinate of the beginning place. It was 5. So this leads to then two differential equations with initial conditions. I'm not going to take the time to solve it here. You can see if you can work it out. I'll tell you what I got. And so what I got was that x of t is going to be 1/2 t squared minus 3 sine of pi t plus 1. And that y of t is equal to t squared plus cosine of pi t, and that was a plus 4. And that is going to give us our x of t, y of t, that is that gives us the path. And if you like, you can graph that. The window that I chose was we're going to use for t values. We're going to go from 0 to 4. And for x, if you choose a window, to go from -5 to 15. And a y value, you can go from 0 to 25. And that will give you that path. All right, if you have trouble with any of these, we can talk about maybe when we zoom in a classroom session, and hopefully that'll get you going.